Good morning, everyone. Everybody hearing and seeing me okay?
Yep.
Yeah.
Good deal. All right. So last time we were in the attempt to finishing up chapter 9, and we ended up having to cancel. And I told you I'd post stuff online for you. I did do that. In fact, I did that night, but oddly enough, I woke up the next morning, it was still uploading because the same problems that were going on with my internet obviously were going on then as well. But I stopped it, erased it, re-uploaded it, and the next time it uploaded in like 20 minutes. So there's now two different videos. I think there's one where I just said for physics 241, and it's basically using center of mass to determine how far a canoe would move when two people in the canoe decided to switch seats. So you got a canoe, you got a person in the seat, and a person in the seat, and this canoe has mass as well. And this person's heavier than this person, and they switch seats. Well, by doing that, conservation of momentum would suggest as soon as you start walking, the canoe is going to start moving the opposite way you're walking. And the same thing with the other person walking the other way. So you're ultimately going to get a net effect where it's moving as long as you're walking. And then when you come to a stop, it comes to a stop. And then it moves again the other direction when the other person's walking. And it comes to a stop when it's that person finishes walking. So the net effect is that the canoe will have moved some net distance. If you use conservation of momentum, you can just figure out what that relative velocity is between the person and the boat, or between the boat and the water preferably, and how long it takes to make that excursion across the distance of 3 meters. If you work that out with conservation of momentum, you would find ultimately how many meters it moved. And what I did was did it by center of mass. So I just assumed that the center of mass would stay in exactly the same spot. And I calculated the center of mass when they're all sitting still initially. Then I set that equal to the center of mass as if the boat had moved. I just arbitrarily, actually not arbitrarily, I intentionally chose the wrong direction from what I physically thought would happen, so that you could see it's okay to guess wrong. And the boat moved to a distance X is what I assumed. And that put the center of mass, instead of being at 1.5 meters, it put it at 1.5 meters minus X. It put the other seat, instead of being at 3 meters, at 3 meters minus X, and then it put the seat that was at 0 meters at negative X. Set those two center of masses equal to each other, solve for X, and I got X equals like negative 0.444 meters or something like that. Anyways, that's a really good problem. It's solved all by itself as one little video clip, and it's like probably well under 15 minutes. So that's one you can look at. Then I held my N05B class, which is my evening class. Or no, it might have been, yeah, actually, I think I held my N05B and my D01C 241 class, which is my Tuesday, Thursday class. Either way, they're on YouTube, and they handle that boat problem again, but I also calculate 2 centers of mass using integral methods. So those are things you should be able to do. I don't want to spend any more time doing that because I'm getting them to you. But if you need to see them done or something like that, then we'll reserve the time at the end of class for anybody to ask questions. I think the video is clear enough and speaks for itself enough to do that. But like I said, I don't want to not give you the chance to see it in real time. It's not that hard, but it is a stepwise process that you got to go through. And there's obviously some calculus involved, and sometimes it's a little scary to people. So feel free, if you need to see any of that, or you just want to see any of that, let me know at the end of class, and I can work it for you then. We're going to start into chapter 10 though. So does anybody have any questions before we move along? Oh, by the way, I haven't set the chapter 10 due dates yet. So I've got to set them today. I should have set them yesterday, but something came up. So I'm going to set the due dates for chapter 10. And remember, we haven't covered anything before after 10, so none of those due dates are relevant. We're going to chapter 36 after this, but that due date's not relevant either. Okay. And the final thing I want to say is some people missed the midterm, And some people did so because they had a valid excuse, and they let me know, and I've set up things for them. But if you have a valid excuse, you can still take it. You just need to let me know and give me some proof that you actually have a valid excuse for missing. If you don't have a valid excuse for missing, I still don't want you to get 0 on the midterm, even though you know, that's sort of the way college works. I don't want to be that guy. I want to be the person that's really working hard to make sure you have every chance to pass. So if you miss the test for no reason at all, you just weren't ready or whatever, I'm going to let you take it, but you're going to lose 10 points. And I've opened it back up, and it'll stay open until Sunday at midnight. So if you haven't done it, make sure you get it done. And you're just going to lose 10 points. And I'll address the grades next week. So anyone have any questions before we get started? All right, so chapter 11 is on rotational motion. And this is where we can now start to think about objects being more than just point particles. So F equals ma was initially solved for a lot of point particles. We pretended blocks on inclines were point particles. We pretended blocks hanging from a pulley were a point particle, and we treated them as separate objects with separate F equals ma's. Then we got into last chapter where we started doing momentum, and we could treat whole objects, but we still didn't take into account how those objects would be moving, like if they're rotating themselves. We didn't take into account that. Well, this chapter allows you to start addressing that, and it allows you to start addressing bigger systems, if you will. So the last one did let you encounter bigger systems, like the train car problem I told you about, where you had a train car with a cannon and a bunch of cannonballs on one end. You fire all the cannonballs to the other end, and you can either use conservation of momentum, or you can use center of mass to calculate how much the train car has moved after all the cannonballs have been moved to the opposite end. So this is just a continuance of that. This is also where we start what we call rigid body motion. So you sort of pretend that the objects can't stretch or contract between 2 points in the object, so they're perfectly rigid. But now you can examine, instead of throwing a ball in projectile motion, you can examine throwing, say, an arrow or a knife or something like that, where it's going to spin, because you have the parabola, the parabolic motion of projectile motion for the center of mass of the object. But then you have, say, an initial rotational speed with which the pen leaves your hand. And if you have that and you have its initial angle, then you can predict anytime later through what angle it's turned. So you can now tell not only where it is along the parabolic path, but also what the orientation of the pen is since it was rotating. That's what some of the things this chapter allows you. Now, the good news is it's not very different from what we already did in kinematics. And in fact, I'm going to show you how basically every equation that we've used in the past has a analog in rotational motion. But I got to start with that idea of arc length equals the radius times the angular measure in radians. Y'all remember that from trigonometry. So let me show you some stuff with that first and make some definitions. So here's my document, Cam. What we studied in trig was basically a circle of radius r. Let's say this circle, which obviously is not that good of a circle, of radius r, if the radius sweeps out an angle theta, then this arc length s from here to here is given by r times theta, where theta is in radians. And obviously, you know that c, the circumference of the circle, is equal to 2 pi times the radius. So clearly, theta is 2 pi for a complete circle. Okay. That also means 2 pi radians, which you can tell by looking at this. This has units of meters, this has units of meters. This is actually just a pure number, so it doesn't technically have any units. So the radian is not really a unit, it really is just a pure number. But 2 pi radians is equal to 360 degrees. Obviously, that's kind of a pain in the butt to deal with, so it's often easier to just state pi radians is equal to 180 degrees. Okay. Now, if you think about that arc length and realize, oh, wait a second, that's just one-dimensional motion, then you can take the equation x equals 1/2 at squared plus v0t plus x0. And you can say, well, wait a minute, this equation should apply to distances going around that circle. And lo and behold, in order to do that, you've got to interpret some things. So for instance, ds over dt, that's the velocity. Does that make sense to everyone? The derivative of the distance you've moved with respect to time is equal to the velocity. Well, if you're actually on a circle, then that r is going to be a constant, and you get d theta dt. And this is defined to be omega, the angular speed. So we've got a new equation, v equals r omega. This one I'll circle, even though it's not a new equation. This one I'm going to box off as well, because it is specifically a new equation. Now, if I take the derivative of velocity with respect to time, we all know that's equal to acceleration. But in this, guys, again, if you're talking about circular motion, that r is a constant, so it comes out in front, and that's a d omega over dt. Well, we define that to be alpha. That's the tangential angular acceleration. Okay, so now we've got another equation. A is equal to r times alpha. So this is called the angular velocity. The one unit that always works is radians per second. There's a lot of times in these equations where we can use other units, but angular velocity in radians per second always works. This has to be in radians as well. And then this quantity is called the angular acceleration. And again, the one unit that always works is radians per second, which you guys also recognize as radians per second squared. In reality, though, I should point out that the total acceleration doesn't have to just be that direction. You can actually, have a car going in a circle, hit its accelerator, and that's going to make this alpha increase. Well, it's going to make this omega increase, but it's basically experiencing an alpha. Okay. But you can also, while driving in that circle, turn your steering wheel towards the inside, in which case you have a center seeking acceleration as well. So in general, the acceleration vector should be equal to the centripetal one, which we'll say is a centripetal in the r hat direction. And then we're going to have the angular one, which is r for any arbitrary r, that's why I wrote it lowercase, times alpha. And that's going to be in the theta hat direction. Okay, so remember, in terms of coordinate systems, this would be x, this would be y, this would be the point right here. Theta hat points that way, perpendicular to that line. This is theta, and r hat points this way. So that's just to keep in mind that, hey, there's other ways you can accelerate, but it's usually obvious what you're talking about by the given problem. So just remember, at the end of the day, there's multiple types of acceleration. You can accelerate by turning your steering wheel in towards the center of the circle or out towards the edge of the circle. And you can also accelerate by hitting your accelerator or hitting your brake. Both of those would result in a change in the theta direction. Does that make sense? So now that we have all that, we can one by one start writing our stuff. What we found initially was we decided that there was a quantity average velocity. That average velocity was equal to delta x over delta t. Well, that turns out to be average angular velocity is delta theta over delta t. But that led us to an instantaneous velocity. V is equal to dx over dt. That leads us to an instantaneous velocity. Omega is equal to d theta over dt. Okay. We also had a concept of acceleration where the average acceleration was equal to delta V over delta T, which led us to the idea of an instantaneous acceleration being dV over dt. Well, guess what? We've got an analog. That analog is the average angular acceleration is delta omega over delta t, and the instantaneous is equal to d omega over dt. If you remember from this equation, when we took a equals a constant, we were able to get v is equal to v0 plus at. Well, the same way we can get omega is equal to omega 0 plus alpha t. If you remember treating this as if it were a constant and this as dx dt, we were able to integrate to get x is equal to 1/2 at squared plus v0 t plus x0. Well, similarly, we can treat this as d theta over dt and assume this is a constant, and then we'll end up getting theta is equal to 1/2 alpha t squared plus omega 0 t plus theta 0. And if you remember from kinematics, we were able to eliminate the t in here by solving this for t and plugging it in here and here. And that allowed us to remove the t, and we end up getting v squared is equal to v0 squared plus 2ax minus x0. Well, it turns out you can do the same thing with this, and you'll get omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. So you see every equation that we've been using, you have an analog in the rotational motion, and the problems even sound the same. If you can just identify the units, you can tell exactly which equation to use in the same way you did it with kinematics. Of course, we also had that average velocity equation when the acceleration was a constant, which is basically all these a equals constant. All those mean alpha equals constant. Okay, but one of the things we found was that average velocity would be v0 plus v1 over 2. Well, guess what? That works here too. Omega average is equal to omega 0 plus omega 1 over 2. In other words, if you just take the average, the numerical average, like their test grades of two velocities, you will get the average speed between the two, assuming the acceleration is a constant. But it gets deeper than that. For instance, we ran into Newton's second law. The summation, and remember this is the way I write it, the summation of forces is equal to mass times acceleration, which is actually a special case. As I told you before, it's actually the summation of forces is equal to dp over dt, right? That's the more general one because that takes into account a changing mass. Well, as you might suspect, there's something analogous to force. Does anybody know what the quote unquote force required to rotate something is? You know what the name for that is? There's even a wrench named after it.
Torque.
Yep, torque wrench. Yeah, so this becomes the summation of the torques is equal to, and there's an analog to M. Okay, that analog is something that acts like inertia, but it actually is more geared towards whether something's rotating to speed up as opposed to whether something is speeding up along a straight line. So for that to happen, it's got to take into account not only the mass, but it's got to take into account the relative distribution of the mass. So it's going to be dependent on the individual mass times the distance from the center of rotation squared. So that's going to be what we call the moment of inertia. I'll put this over here and I'll replace the M with the I, that's the moment of inertia, and I'll place the A with the alpha. And in this, I'll say torque is defined to be R cross F. So in other words, you take a cross product of a vector that points from the center of rotation to the application point of the force, cross product that with the force, and that'll be the torque, the individual torque that you're going to use. And then I is going to be defined as the summation over I of M sub I R sub I squared, which actually becomes the integral of R squared dm. So that's something that's looking more and more like center of mass. So now I'm going to address this one. I'll blank it out here because I had to use so many lines here. I'm going to say the summation of the forces is equal to dp dt. There's an analog for that too. And it's the summation of the torques is equal to dl over dt. Remember, P was defined to be mass times velocity. Well, one way to define momentum, angular momentum, L is equal to R cross P. But just like L could be M times V, you can also see L would be I times the equivalent of I is M, or the equivalent of M is I, the equivalent of V is omega. So it's also I omega. So that's the kind of stuff that we have at our disposal, just from the structure of kinematics being independent of what direction you're going. All that really matters is the distance along the path that you travel. The first derivative of it being a type of velocity, the second derivative of it being a type of acceleration. So now you have more or less a complete picture of all the different things we can do. So let's start off by doing some simple calculations with radians, just because we know you've used them before, but it's always helpful to go back and examine them. So for instance, radian is a measure of angle. So you know that 2 pi of them equals 360 degrees. You know that pi is equal to 180 degrees. You might even know that 1 radian is like, if I remember correctly, it's like 54.7 or something degrees like that. Those are all helpful issues, but let's examine some everyday problems. Let's imagine, for instance, that the Narendra Modi, are y'all familiar with that stadium, Narendra Modi Stadium? It's the world's largest stadium. It's built in India, and they use it mostly for cricket, as you might suspect, but it's got tennis courts in it. It's got, you know, the ability to do tennis tournaments. It's got the ability to do soccer tournaments, but it's probably one of the largest, width-wise, one of the largest structures man-made on the surface of the earth, other obviously than the Great Wall of China, which I looked up this morning and I can't believe it. I might be right, I might be wrong, but according to the interwebs, it suggested the Great Wall of China has a length of 13,171 miles. Now I know that's a curvy length, so it's not like it's a straight line, 13,171 miles, but I'm still flabbergasted to think that that's the real figure. Does that sound like the real figure to you guys? So we're going to go with that anyways on another problem. But what I want to do right now is think. Some people are bothered by ideas of moon landings and stuff like that. They think, I mean, there's actually some people that believe they were fake and stuff like that. Delaney says that is about right, so that makes me feel a little better. Having never looked it up before, I'm astounded still. But one of the things they sometimes say, and this is really the shallow end of the gene pool that's making the clay, and I guess one of the things they say is, we can't see any of the stuff we left there. Well, yeah, that's because the moon is really, 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 really far away, right? So what if we put the Narendra Modi Stadium on the surface of the moon? Would we be able to see that with our eye? So could we see the Narendra Modi Stadium on the moon from the Earth with the unaided eye? And then I'll say Hubble. Okay. So it turns out the eye has a angular resolution. So I'll say theta min for the eyeball is 28 arc minutes. And that means like the perfect age person who hasn't got any problems with their eyesight or anything. So we're maybe talking, an 18-year-old that hasn't been lifeguarding on the ocean front has perfect 20/15 vision or something like that, right? So they can actually see something if it's 28 arc minutes wide. So what we want to do is calculate how wide in arc minutes would the Narendra Modi Stadium be. Well, ideally what I would have done, but I didn't have much time because I was having some computer difficulties this morning. What I would have done is went to Google Earth, typed in Narendra Modi. Any of y'all want to do this in real time, it'd be greatly helpful. But you can type in the Narendra Modi Stadium and then use the little ruler and measure what's the largest dimension across it. Because I'm going to make an estimate, because what I do know is that the Narendra Modi Stadium is 63 acres. Okay. Now, I doubt that it's like, 800 meters by 4,000 meters or something like that. But I also doubt it's square. But if we take it as roughly square, then I can get a pretty good idea of what the diagonal is, and that's a good order of magnitude of approximation. So 63 acres means 63 acres times 1 acre. I happen to know off the top of my head because I'm a weirdo. Happens to be 43,560 square feet. That's from my life in civil engineering work. So I know that, so I can tell that that's basically that's basically the square feet. And when I do that multiplication, I do 63 times 43560, and that gives me 2.74, carrying one extra digit there, times 10 to the 6 feet squared. Okay. So what I'm going to do is I'm just going to take the square root of that and assume that it's basically the square root of this times the square root of this across. And then I'll multiply that by the square root of 2, and that should roughly give me the diagonal. So I'll take the square root of this. And I get 1.66 times 10 to the 3rd feet. And then I'll do square root of 2 times the square root of the area. And that should give me roughly the diagonal. The biggest dimension, in other words. So I'm going to say that's 2.34 times 10 to the third feet. Now I want to go ahead and convert that to meters. So I'm going to say 2.34 times 10 to the third feet times 1 foot is equal to 12 inches times 1 inch is equal to 2.54 centimeters times 100 centimeters is equal to 1 meter. So now I'm down to meters, which is really what I wanted. So now I'm going to take this, multiply by 12, multiply by 2.54, and then divide by 100. And I get 714 meters roughly. Okay, now really in order of magnitude calculation, you probably just, if you want to be on the safe side, because maybe the thing's not square, is maybe you would say 800 meters. Or if you wanted to be a little more strict, maybe you round this to 700 meters, but normally you use just 1 sig fig. So what we got to realize now is our eyeball is sitting on the surface of the earth like this, looking way out here at the moon. And there's a distance across here of 714 meters. Okay. So what I'm seeing is that angle right there. And I can use the fact that S equals R times theta is a pretty good approximation, because obviously when you're looking at a small chunk like 714 meters of the surface of the sun, or excuse me, the surface of the moon, that's a small fraction of the circle, so it's fairly flat. And actually, if you spread that over a distance of, the distance to the moon, then you also see that that is pretty flat that way. So we can actually use this. So what I'm going to do is I'm going to say theta is about equal to S over R. Now S would be the 714 meters. Now I need to divide that by the distance to the sun, which we know is a little bit over a light second. And in fact, I will pull that up. The Earth moon distance, and I keep saying sun, I don't know why, 3.84 times 10 to the 6, or excuse me, 384 times 10 to the 6 meters. 384 times 10 to the 6 meters. And that's going to give it to me in radians. Then I just got to do some converting. So 714 divided by 384 e to the 6 gives me 1.86 times 10 to the negative 6 radians. Okay, now I can need to convert that to arc minutes. So what I'm going to do is, first off, I'm going to take and divide it by 2 pi and multiply it by 360, or I can divide it by pi and multiply by 180. So I'll say, let's take this number and divide by pi, multiply by 180. That's going to get it to degrees. And then I'm going to divide it by 3600. Or excuse me. Yeah, that'll get 2 degrees. And then I know that 1 degree is equal to 3600 arc seconds. So I'm going to do that. So what do I do when I get that? Or what do I do when I do that mathematics? I'm going to take the number I first divided by pi. And then I multiply it by 180. Then I divide it by 1, and then I multiply it by 3600. So that gives me 0.384, 0.384 arc seconds. So the answer is no, or hell to the no, in the words of Medea. Okay. So any questions on that? Now let's see what the angular resolution of Hubble is. I used to know this off the top of my head.
What was the thing up there at the beginning? It was like three acres or something, or is that a
63
symbol
acres.
next to it? 63. Okay, the 6 looked a little weird to me.
Yeah, my sixes
Gotcha.
and 9s are the same thing, but they don't look right. Okay, so basically the arc second, or actually the resolution of the Hubble. Hopefully y'all can still see where I'm writing. Yeah, you can. Theta min for the Hubble is equal to 1/20th of an arc second. So if you know about 1/20th, if you multiply this by 5/5, you'll get 5/100. So that's basically 0.05 arc seconds. So yeah, this the Hubble could actually see the Narendra Modi Stadium. So Hubble, yes. Probably a lesser telescope, and there's a lot of lesser telescopes, by the way. A 12-inch telescope, there's a specific formula we can use that calculates the diffraction limited resolution. And even if you took a nice 12-inch telescope, which if you got all the bells and whistles would probably cost you 12 grand. If you just got, say, a 12-inch Dobson telescope, that's still going to cost you about $1,000. So if you use one of those, my suspicion is that angular resolution for a 12-inch is not enough to see this. So I'm checking out 12-inch resolution. The good news is the larger the diameter of the telescope, the better the resolution. The bad news is it's only like 1-to-1. So if you double the diameter, you only make the resolution twice as good. But I'm trying to look for an actual resolution. Of course, and this is the best case scenario. A 3-inch telescope would have a resolving power about 1.5 inches arc second, excuse me. And then a 12-inch telescope, which should be 1/3 more than an 8-inch. So we said the 8-inch telescope was 0.57. So I added maybe a 0.2 to that, 0.77. So a 12-inch telescope would require it to be 0.77 across. And therefore you couldn't see it with a very high quality 12-inch telescope would not be able to see the world's largest stadium on the surface of the moon. Okay. Now recently I saw a meme on Facebook, because that's where all the evil memes exist, where a recent Chinese astronaut rode on the International Space Station and discovered he could not see the Great Wall of China from space. Now, the International Space Station actually orbits at about 264 miles above the surface of the Earth. No, 254 miles above the surface of the Earth. And the human eye, again, can see about 28 arc seconds. In other words, it has to be at least 28 arc seconds across to see it. So you could use that 13,171 miles and that 251 miles and do the same calculation to see whether or not you could see it. Now, what they actually reported is that if the sky is crystal clear and you're in low Earth orbit, which, believe it or not, low Earth orbit is the first 2,000 miles, or excuse me, the first 2,000 kilometers, which is more like the first 1,600 miles, then you could barely make out the Great Wall of China. So y'all can try to verify that if you'd like. That's a very typical calculation for this type of scenario. Does anybody have any questions on that? All right, so now that we have that, we can also try some more mundane problems, like let's say just the simple stuff like we used to do in kinematics. Let's say a record player which y'all don't know, but it's like the predecessor to a CD player. which y'all don't know, but that's like the predecessor to an iPhone. So a record player basically had these discs that were maybe this big, like 8 inches across, but like also up to like 16 inches across, and they spun very slowly. For instance, one of the speeds was 33 1/3 revolutions per second, and they had little grooves cut into them, and those little grooves would cause this little needle, sort of like the tip of this pen, to go and tweak just the right way. And that little tweak that it did would actually make the music and the voices that you hear. That was the way a record player used to work. So let's say a record player on 33 1/3 is initially spinning at 1 revolution per second. Okay. How long will it take? Whoa. Don't know what happened there, but I can't erase. I forget that I have an erasable pen. How long will it take to reach 33 1/3 revolutions per minute? Actually, this is 1 revolution per minute. How long will it take to reach 33 1/3 revolutions per minute if its acceleration is, let's say, 3 degrees per second per second? And B, so that'll be part A, through how many revolutions and degrees and radians will it rotate while accelerating? Okay, so a record player set on 33 1/3, that means 33 1/3 revolutions per minute, is initially spinning at at 1 revolution per minute. A, how long will it take to reach 33 1/3 revolutions per minute if its acceleration is 3 degrees per second every second? And B, while accelerating, through how many revolutions, degrees, and radians will it rotate? In other words, I want you to work it out for all 3 units. Okay, does everybody sort of get an idea what that means? What equation are you thinking you would use if this was a car is initially driving at 1 meter per second and it needs to reach 33 1/3 meters per second, and its acceleration is 3 feet per second per second? How long will it take? What equation would you use then? So I gave you an initial velocity, I gave you a velocity that I wanted, and I gave you an acceleration. That was when I was telling you it in linear units, basically. So now we're doing rotational units. So all you got to do is figure out what equation you would use in that linear problem, and you can use the equivalent one in the rotational problem. So has anybody thought about what equation they want to use?
No, V equals VO plus AT. Do you don't have a time? Yeah.
Yeah, so omega is equal to omega 0 plus alpha t, which was the equivalent of v is equal to v0 plus at, right? So that's really all I'm trying to do by giving you these parallels, is you can sort of translate this back to your own language. And you try to keep track of things like, notice this degree per second was different from revolutions per minute. That's why I put that in feet per second, and this one in meters per second. So what we have is omega 0 is equal to 1 revolution per minute. What we want is omega to be 33.3 revolutions per minute, and we know alpha is equal to 3 degrees per second. Okay, obviously something's got to give, because we've got all sorts of whacked up units here. We can see that if I had revolutions per minute here and multiplied by minutes, that would actually give me revolutions per minute. But the problem is I have like a revolutions per minute per second, or degree per second, stuff like that. So this has the units that that work with this. So really I got to change the units of this to make things work. And I don't have to do radians, but I could. If I just converted everything to radians and seconds, then it would automatically work. But you don't always have to do that. If you want to, first ride with training wheels, then by all means convert everything to radians and seconds and go from there, and that's fine. But over time, you'll learn when you can and can't do it. So we've asked for part A, we've asked for the time, and we can see that the time would be omega minus omega 0 over alpha. So what I'm going to do is I'm going to make 3, which is the alpha, 3 degrees per second. I'm going to say, okay, well, 360 degrees is equal to 1 revolution. So that'll actually get me to revolutions per second. But now I can say, wait a second, I would probably want to know this in seconds. So if I get rid of one of these seconds and make it minutes, but then keep the other one, then that would be golden. So I'm going to say, change this second right here to minutes. And I'd say that 60 seconds is equal to 1 minute. And then I'd ultimately have revolutions per minute per second. And that's sort of the best case scenario. So I'm going to do 3, and I'm going to divide by 360. And then I'm going to multiply by 60. And I get 0.5. And that's revolutions per minute per second, which is really the best of all the things I can possibly come up with. Okay. So now I'm going to say T is equal to 33.333. I'll keep a few extra digits because it said 33 1/3. So I'm keeping a few extra digits basically. That's revolutions per minute minus 1 revolution per minute over 0.500 revolutions per minute per second. So I just do basically 33.333 minus 1. And then I divide that by 0.5, which is the same thing as multiplying by 2. And I get 64.66. And that's seconds. And really, I should probably, since I only used 1 sig fig there, I'll pretend like this was 2, and I'll pretend like this was 3. So I'll just say this is about 64.7 seconds. So any questions on that one? So it would take over a minute to actually get up to that speed. So obviously that's not an ideal acceleration, 3 degrees per second. But let's go ahead and look at part B. Now part B wants to know through what angle it actually rotated. So what I might say is how many meters did it travel while it was actually accelerating at that rate from 1 meter per second to 33 1/3 meters per second? What equation then would you think about using? You could use v squared equals v0 squared plus 2ax minus x0. But you could also use x is equal to 1/2 a t squared plus v0 t plus x0. However, using the second one would require us to use the time that we just found. Had you been doing this on a test and I was just grading on whether you got the right answer or not whether you did it correctly, then you get 0 credit if, for part B if you did part B this way and had gotten the wrong answer for part A. So we try to use the thing that we didn't, that doesn't have a variable we calculated. So it'd probably be better to use this one. So the equivalent to that is omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. And when I do that, I'm going to make some assumptions. I'm going to say theta 0 is 0. I'm going to say theta is what we want to know. I'm going to say omega is equal to 33.333 revolutions per minute, and omega 0 is 1.00 revolutions per minute. So I could ultimately calculate theta as follows. So this is 0. So I'm just going to get omega squared minus omega 0 squared over 2 alpha. And that's going to be equal to my theta. And that's because the theta 0 is 0. So I'll type 33.333 squared. No, actually, I should follow that this is revolutions per minute squared. Okay. Minus 1.00 squared over 2 times. Now, here is where I'm going to sort of break my rule. I'm going to use this conversion I've already done, but that's okay because I had to do that no matter what. So I'm going to say that 0.500 revolutions per minute per second. Okay. So this is going to be revolutions per minute squared. I'm going to end up dividing revolutions per minute squared. That's a revolution squared per minute squared like this. Actually, like this. And I'm going to divide that by revolutions per minute per second, which is the same thing as revolutions per minute second. So I flip that over and I'll get revolutions right here and then minutes here times seconds here. So you see, that's kind of a problem. Obviously, I'm going to get revolutions, but now I'm going to get seconds times minutes, or excuse me, seconds divided by minutes. So that doesn't really work too well for us in this unit scenario. That makes sense? So what I have to do now is, if I want to use this equation, I need to further convert that to revolutions per minute per minute. So we'll say, no, let's do alpha is equal to 3.00 degrees per second, which equals, here's where it's good to just use the mathematics of a unit so you can just see what it is. So I'm just going to call it seconds squared. So what I want to convert this to is degrees per minute per minute. So I'm going to say, all right, well, or excuse me, revolutions per minute per minute. So I can say 360 degrees in the bottom will cancel degrees in the top, and I'll say that's 1 revolution. So that gets rid of the degrees and replaces it with revolutions. Now I've got a second times a second here, so I know that 60 seconds is equal to 1 minute, but I've got seconds times seconds, so I need to square that. So you can see actually what happens is I'm going to get 3,600 divided by 360. So this just becomes 30.0 revolutions per minute, or minute squared, either way you want to write it. So that's kind of a nice little happenstance. So now I can write it again. Theta is equal to 33.333 revolutions per minute. This time I'll show you, since I didn't actually take the time to show you there, minus 1.00 revolutions per minute squared over 2 times 30.0 revolutions per minute squared here. So you can see the revolution is going to be squared up top. The minutes are going to be squared at the bottom. The minutes are squared on the bottom here, so they automatically cancel out. The revolutions are single, so I just get revolutions out, and that works just fine. Okay. So now I'm going to take 33.333 squared minus 1 squared, and then I'm going to divide that by 60, and that gives me 18.50 just plain revolutions. So that's one answer. That's also, of course, equal to, I asked for revolutions and degrees and radians. So 1 revolution is 360. So I'm going to multiply that by 360. And I'll say that, ooh, the devil's number, 6.661 times 10 to the 3rd degrees. And of course, I can also turn this revolution into radians by multiplying it by 2 pi. And I get 116 radians. So those are all the answers for part B. Any questions on that? Now our time was technically up about 9 minutes ago, but at least we got a couple decent problems solved. And that's what I hate about 50-minute classes. An hour and 15 is so much better. But anyways, if anybody has any questions, please stick around. Remember, I did open the midterm for those of you who might have missed it. You are going to get 10 points off unless you can give me a valid and verifiable excuse. So if you missed it, don't take a 0. And that's what's going to happen if you don't take it by Sunday at 11:59 p.m. But be advised, you are going to lose 10 points unless you have, like I said, a verifiable excuse that you can show me the excuse for. Okay. Don't forget, homeworks are due. Again, I think we have it might be like chapter 8's due this Sunday or something. Who knows? I'm going to set the date on chapter 10 soon, so pay attention to that. And I'll wait for the last of you to leave in case anybody wants to see how they calculate a moment of inertia or any of that kind of stuff, or excuse me, a center of mass. That was what I told everybody I'd do.
I was one of the students that had a problem with the midterm, and by problem I mean the practice test. You enabled the Chromebooks to take the test, and then on the real test it wouldn't let me do it on a Chromebook.
Okay.
So that's why I didn't email you, because we did the practice test and I was like, of course it doesn't work on the real test, but the practice test was fine.
Gotcha. I seem to recall getting an email from someone named Dawson. I remember because I thought it was my student from a couple semesters ago. Sorry about that.
That's okay.
If I find out that my Chrome setting was like that, then I'll definitely let you. You still have till Sunday to take it, and I won't take any points off. Okay.
But the problem is that as long as would it be good to take now? Because that's the only computer I have with a camera.
Yeah, let me go ahead and double check what that is, and I can change it right now too. So that'll be good. And you said the practice wasn't a problem, so that should be that should take care of it. I can't believe I didn't do that because that's one of the first things I always do on these finals and midterms. Okay, so let's see here. I do have it set to October 24th, 11:59 p.m. So that's good. Now I'm going to go to my lockdown browser area, and I'm going to check and see whether that setting is okay. That's the problem with these respondus stuff is I got two websites I got to go to, both of them through Canvas, and one has a bunch of controls that can sort of override the other one. So that makes it a little bit complicated, but let's see, settings.
Yeah, I had the same problem with my chemistry class. That's why, like, I knew immediately when it came up. I was like, "Oh no!" I was like,
Oh no! Oh no!
It was like the same error message. I was like, "Oh."
Well, that stinks. Let's see, advanced settings here. Lockdown browsers in the App Store. Lock students in. Require lockdown browser feedback. I don't even see that setting anymore, and I've checked it every time, so I know it's here. I just got to find it. This is weird. Tour.
The weirdest part is, so for my chemistry class, when this error message came up, it was like, it wouldn't even let me into the test. But this time I got to like record my workspace. I checked off all the boxes, and then I went to like advance to the test, and then it was like Chrome OS is not responding. And I was like, what?
That's weird. It's it doesn't even show the word for Chrome anymore. It used to have a thing where you had to check and say, well, allow it to take it on a iPad, and then it had a setting for allow a Chromebook, and those settings aren't even there anymore. Or respondus lockdown browser. That's set. Require respondus monitor. That's set. Yeah, it's not even giving me that option anymore. Any way you can take it at a testing center?
Yeah, I was about to say I can like find a webcam or something and just like plug it into a USB port on my laptop or something. But
Yeah, try that with that, or if you can't do that, then let me know and I'll set you up with a proctor at one of the testing centers, whichever campus is closest to you. Because yeah, it's not giving me that.
Right,
I'm thinking they finally updated it where Chromes are automatically able to be worked. But yeah, if you had a problem, you had a problem.
So yeah, okay, maybe if they updated it, I'll still try, and then I'll see what happens.
All right, thanks.
All right, thank you. Bye.
Anybody else have any questions? Mr. Roberto? Nope, that's it.